Section 10.5, the ratio, root, and comparison tests. All right, we have three different tests here. We've already done the integral test, and it's a great test because it can tell you if it converges or diverges, but it can't integrate things that have factorials in them. That's going to be a problem. So the first test we're going to look at is the ratio test. It's actually my favorite test. It says if you have a summation of a sub k's, and you let r equal the limit as k goes to infinity, so you're adding them all up, of the k plus 1 term over the kth term. So you're taking the kth term and you're putting it under the next term. If you take that limit, three things. If 0 is less than or equal to r is less than 1, the series converges. Second thing, if it's greater than 1, including infinity, the series diverges. And then finally, if it equals 1, the test is inconclusive. So test fails, which means you would have to go and use a different test to prove that. Okay, so looking at example 1, we want to use the ratio test, part A, for k equals 1 to infinity, 10 to the k over k factorial. So we set it up, and I don't usually use the r on this, so I'm not going to write r. We're taking the limit as k goes to infinity. We are taking the kth term, which is just what you see there in the series, in the summation, on the bottom, and on top it's the same thing except you change all the k's to k plus 1s. And now we're going to use a regular old elementary school division. That middle line is the division sign, so we need to flip over the denominator and multiply. So we're going to have 10 to the k plus 1 over k plus 1 factorial times k factorial over 10 to the k. All right, looking at the tens, there is one more 10 on top than there is on the bottom. So I could cancel this guy and this one and leave 1. So this is gone. This is a 1. Now, on the factorials, I could take, let me just take k plus 1 for a second, factorial, and show you something. That's the same as k plus 1 times k minus 1, and so on, all the way down to 1. So if we break off the k plus 1, the part that's left there in the brace, that's actually just k factorial. So if I do that, the k factorial is going to cancel. So I have k plus 1 times k factorial. This cancels with this. So what do I have left? I have the limit. As k goes to infinity, there's a 10 on top. There's a k plus 1 on the bottom, and as k gets large, the bottom gets large, this thing is going to 0. Well, 0 is in number 1's choice. R is between 0 and 1, including 0. And so that means that this converges. So I'm going to write series converges by the ratio test. Part B. K equals 1 to infinity, k to the k over k factorial. Factorials, the ratio test is amazing for factorials. Those things wipe out really nice. So this one is the limit as k goes to infinity. It's going to be k plus 1 to the k plus 1 over k plus 1 factorial over k to the k over k factorial. So fixing this as multiplication, I have k plus 1 to the k plus 1 over k plus 1 factorial times, flip that guy over. So now, what can I do with this? Again, I can wipe out the factorial. This will wipe out and leave a k plus 1 down here. Now, on the top, I have no place to write this, so I'm going to take a new step here. I'm going to write that k plus 1 to the k plus 1 as k plus 1 times k plus 1 to the k. I have a k plus 1 on the bottom, and I have a k to the k. I did that. I took off one of the k plus 1s so that I could now cancel these out. And now this is actually k plus 1 over k to the k, which would then turn into one plus 1 over k to the k. Now, way back in chapter 7.6, we had a rule that I said we needed to memorize. It's actually the definition of E. And it is 1 plus 1 over k to the k is equal to E. So if that's the case, then this whole answer just turns into E. E is 2.7, so it is larger than 1. So the series diverges by the ratio test. Oops. This next test is called the root test, and it's exactly the same as the ratio test, except it says that we can just examine the stuff inside the root. If I have a kth root, if I have something to the kth power, so I can take the root of it and just look at the stuff inside, and the rules are still the same. So let's look at example 2. The summation, this is part A. That's a pretty sad summation sign. K equals 1 to infinity of 4k squared minus 3 over 7k squared plus 6 to the kth. So it says that we are supposed to take the limit as k goes to infinity and take the kth root of it. In other words, what we're doing is we're saying we don't have to even look at the exponent, we can just look at the stuff inside. Because if I take the kth root of something to the kth power, the k's cancel, so now I'm down to the limit as k goes to infinity of 4k squared minus 3 over 7k squared plus 6. The exponents are the same, or I could use L'Hopital twice, but the exponents are the same, so I look at the coefficients and I get 4/7. 4/7 is between 0 and 1, so the series converges. I'm going to write less than 1 here, even though it's got to stop at 0. Okay, part B wants us to do the summation k equals 1 to infinity 2 to the k over k to the 10th. Okay, so if we're looking at that one, the limit's going to turn into the limit as k goes to infinity of the kth root of 2 to the k over k to the 10, which turns into the limit as k goes to infinity of 2 over, and this would be k to the 10 over k. if I write it with a fractional exponent, which I could then turn into the limit as k goes to infinity of 2 over k to the 1 over k to the 10th. And we have to recall that the limit, and I'm going to write it over here,